The problem tackled here is that of an autonomous robotic agent navigating an unknown and dynamically changing environment without the use of a global map. Static obstacle navigation solutions include potential fields, which are efficient and produce safe but often incomplete paths, bug algorithms, which have a completeness guarantee but rely on geometric holonomic control, probabilistic roadmaps, which have a greater flexibility in considering alternatives, which leads to a completeness guarantee but requires a global map. They are also computationally wasteful and paths may be convoluted. Dynamic obstacle navigation is more difficult due to the uncertainties in future obstacle states. Potential field incompleteness remains, and the bug and probabilistic roadmap completeness guarantees can no longer be given. Our novel and significant contribution here is to combine the strengths of the mentioned three types into a single deterministic approach while mitigating their weaknesses and dealing with dynamic obstacles. We provide a completeness guarantee for short and smooth solutions that allows non-holonomic control. SpiderBUG was tested with the physics simulation software PyBullet in 3 experiments. The first determined the best combination of tolerance hyperparameters, and results support the hypothesis that higher values lead to better performing paths. SpiderBUG was designed with deterministic non-holonomic movement systems in mind. The second experiment confirmed that the planner is also applicable to holonomic vehicles, and can even cope to a limited degree with non-deterministic motion, simulating extreme movement noise. Results from the last experiment show that SpiderBUG is indeed dependent on its geometric calculations, which assume linear constant obstacle motion. As expected, random accelerating obstacles or obstacles which change direction cause the planner to perform less well. A possibility for future research exists here. In this demonstration, both the robot state in the PyBullet simulation and the internal planner state are shown, however, occasionally sped up. First, the motion-to-goal behavior is used as SpiderBUG maintains a set of high-quality goal-connecting paths through the use of a dynamic web. The web is maintained in 3D spacetime, compensating for estimated obstacle trajectories. Here, the motion-to-goal's exit condition is satisfied as path lengths increase past the threshold, causing the boundary following behavior to be engaged. Here, the planner begins to briefly switch between modes as sensing and obstacle motion uncertainties trigger behavior exit conditions. This is expected, and SpiderBUG continues to perform well due to the introduced tolerances. The planner completes in the motion-to-goal mode and reaches the goal.